talk about Newton's 3 laws. And the first thing we're going to do today is we're going to talk a little bit more about mass and weight and how we can calculate them and distinguish between them. And then we're going to start talking more about these vector diagrams or free body diagrams. So we'll be talking about the types of forces that you need to be able to identify and be able to draw in different diagrams. So first of all, we talked about mass last time, and we talked about it as being a measure of the inertia of something. The more mass it has, the more of a tendency it has to stay doing whatever it is doing, being at rest or traveling at a constant speed. Mass is measured in kilograms. Weight, on the other hand, is a force on a mass due to gravity. So if we were to look at F equals ma, the force that we're talking about is our weight, which is Fg. And that is the force that makes something accelerate at negative 9.8 meters per second squared. And in these problems, we will not be so hung up on the negative right now. We're just going to look at the absolute value. So, for example, if I have a mass of 1 kilogram, its weight is 1 kilogram times 9.8 meters per second squared, which is 9.8 newtons. So, if I double the mass, right, then I double the weight. But remember that the weight depends on gravity. And this is gravity for the Earth. So on Earth, the apple weighs 9.8 newtons. But on the moon, gravity is only 1.6. So its weight on the moon would be 1 kilogram times 1.6 meters per second squared. So it only has a weight of 1.6 newtons. So weight changes. But notice what did not change. Mass. Mass is how much stuff you're made out of, is the amount of matter in the object, is the amount of electrons and particles and atoms, and it is constant from place to place. Now, let's say that I tell you that I have a 200 Newton box. You should be able to distinguish that 200 newtons is a weight. And if I ask you to find the mass of it, I'm going to use the weight equation, Fg equals mg, and I'm going to solve for mass. And it's going to be Fg divided by gravity. Since we're on Earth, we're going to use 9.8. So I've told you the box is 200 newtons, which is 9.8 meters per second squared, and 200 divided by 9.8 is 20.4 kilograms. So it's 20.4 kilograms. If I had said instead that this is a 200 kilogram object, you should recognize that as the mass, and that to find the weight would simply be 200 kilograms times 9.8, which is 1960 newtons. So this is something that you need to be able to go back and forth from. All right, so let's start our talk about forces and drawing force diagrams. And the first thing we're going to do is we're going to talk about that normal force that we talked about earlier, the force of the surface supporting an object. So our simplest example is a box on a table. So we're just going to number these A, B, C, and D, and then we'll draw pictures of them. So let's say that we have a box sitting on a table. So we're going to imagine that all of the mass is in the center of mass. So we're going to draw a dot there. And then we're going to label the two forces that are acting on this. Well, first of all, there is weight. And weight always works perpendicular to the floor, straight to the center of the earth. It's not falling through the table. It's not unbalanced. It's balanced with the force of the table on it, or the normal force. So if the weight is 200 newtons, then the normal force is 200 newtons. That's the simplest thing, right? What if I push on the box? Okay, let's say that I push down on the box. So let's say it's still the 200 Newton box. Let's say that I push down on it. So now we have an applied force. We're going to call that FA. And let's say that I push down with a force of 20 newtons. Well, it still has a gravitational force, always acting down, of 200 newtons. How does that change the normal force? Well, now the floor has to support both of those, right? If this is an equilibrium and it's just sitting there, then all of the forces have to add up to 0. So this one force is really 220 newtons. So this means that this has to be, my normal force has to be equal to 220 newtons. If instead I pulled up on the box with 20 newtons, so let's say I'm pulling up on it with 20 newtons, the weight of it is still 200 newtons. But what does the floor have to support? Well, you're already supporting 20 newtons of the 200, so the floor has to support 200 minus 20, or 180 newtons. So the normal force is not always equal to the weight. You have to take into account the situation. So let's talk about pulling a box with a rope. So in this case, what we're going to do is we're going to have a 200 Newton box, and we're going to pull it with a rope that has a tension of 100 newtons at 30 degrees. So let's talk about what's happening. So what I'm going to do here is I'm going to draw in my weight vector, and I'm going to draw in my rope. And it has a tension of 100 newtons. And it is making a 30-degree angle with the table. So what does that mean? Well, I'm pulling at an angle, which means that I am pulling it to the right. So it has a X component and it has a Y component. This is what we call tension. I'm just going to call it T. So it has a TX and it has a TY. So I'm doing two things, right? I'm pulling it to the right and I'm lifting up. So in the Y direction, it's in equilibrium, which means that the normal force plus TY has to be equal to the weight. So in the Y direction, Fn plus Ty has to be equal to Fg. Well, let's find Tx and Ty. We know how to find components now. So Tx is just going to be 100 times the cosine of 30, which is 87 newtons. And Ty is going to be 100 times the sine of 30, which is 50 newtons. So the normal force is going to be equal to Fg minus Ty, or 200 newtons minus 50 newtons. So the table only has to support 150 newtons. Now in the X direction, what's going on? The only force acting on it is Tx, and that is going to make it accelerate, right? Because there's nothing, it's unbalanced in the horizontal direction, right? There's nothing balancing Tx because there's no friction on this. So Tx is 87 newtons, and that is equal to the mass times the acceleration. Oops, the mass. Well, do I have the mass of this? can I find the mass? Well, I know that weight is equal to mg and mass is equal to the weight divided by g. My weight is 200 newtons, gravity is 9.8, and we found that to be 20.4 kilograms. So I'm going to plug in Tx is 87 newtons and 20.4 kilograms times acceleration. My acceleration is going to be 87 divided by 20.4, which is 4.26 meters per second squared. So it's going to accelerate in the x direction, and it's going to accelerate at 4.26 meters per second every second. Now, in a problem like this, when you draw your diagram, I'm going to want to see the x and y components, and I'm going to want to see you do an analysis of what's going on in the y direction and an analysis of what's going on in the x direction. In the y direction, all of the forces add up to 0, but in the x direction, they don't, right? They're unbalanced. They equal Tx. If they all add up to 0, then that means all the upward forces are being bounced by the downward forces. Let's look at a couple of others. Let's talk about another example of a box on an incline. So we're going to call this one A, B, C, D, E, and this one F. So for E, we're going to talk about the inclines now, and we're going to spend some time talking about it because this is something that we'll be seeing a lot. So I'm going to draw my incline plane like a wedge, and let's say that it has an angle of 30 degrees. And I'm going to draw my box up sitting on it at an angle. Remember that weight always acts down perpendicular to the floor, and that the normal force is the surface pushing up on the box, which is not going to be equal and opposite to the weight because it just can't. But you do see that the weight can be resolved into a component that's perpendicular to the incline and parallel to the incline. And right now we're taking friction out of this simply because it makes it easier for us. So we have these forces. So what is Fn equal to? Well, we're going to kind of rotate this around, and this is going to be this is going to be the x-axis, and this is going to be the y-axis. So in the y direction, all of the forces are adding up to 0. So that means that the normal force has to be equal to the only other force along that direction, which is F perpendicular. And in the x direction, they're unbalanced, which means that there's going to be acceleration. And the only force that's causing that is F parallel. It causes it to accelerate. So let's talk about how we find F perpendicular and F parallel. Turns out that by similar triangles, if I were to kind of draw this little right triangle down here, this is our little right triangle, that this angle is opposite the height of the weight triangle. So it's going to be, by similar triangles, geometry, this is going to be 30 degrees. And notice that F perpendicular is adjacent to 30. So what we're going to do is we're going to use the hypotenuse of that triangle, and we're going to take cosine of 30 to find F perpendicular. So F perpendicular is going to be equal to FG times the cosine of the angle of the incline. And that makes F parallel FG times the sine of the angle. So if I want to know Fn, I'm just going to find F perpendicular, which is going to be the weight, and this is still a 200 Newton box. So 200 newtons times the cosine of 30 is going to be 173 newtons. And F parallel is going to be, just plugging in for my equation up here, 200 newtons times the sine of 30 And that's going to make our mass, which we found earlier to be 20.4 kilograms, accelerate. So 200 times sine of 30 is 100 newtons. And it's going to make the 20.4 kilogram object accelerate. So if I divide both sides by 20.4, I get 4.90 meters per second. So do you see how I did this? First of all, you guys can definitely have this on your cheat sheet on your tests. This would be what I put on the note card. You're always going to have this diagram here. It's always going to be drawn like with F parallel, F perpendicular, Fn, and Fg. And you can write down these equations so you don't have to memorize them. But what you do need to memorize is that Fy and Fx, you need to memorize the problem solving strategy here, which is draw your vector diagram, label the vectors if they have components, find all the values of the vectors if you can, and then look at what's going on in the y direction. If it's balanced, all of those forces add up to 0, and that means that the upward forces are equal to all of the downward forces. And in the x direction, if they don't add up to 0, then they add up to mass times acceleration. And then you need to identify what the forces are along the x direction that are involved in that. There's only one force, F parallel, and then you that's going to be equal to ma. And then you can find some useful information. All right. Oh, I'm holding up a picture. Okay, so let's just hold off on that one right now, and we'll do one like that later. All right, so let's talk about the applied force. So the applied force, we've